and UCL. And he did a PhD at University of Technology, postdoc at UCL, and now has a tenure track position at Oulu, and also received a Finnish Academy postdoc early career fellowship. Research. So he's going to talk on reduced models in learned image reconstruction.
Well, thank you very much for the introduction. Maybe a small addition. The previous speaker was my PhD supervisor, but I'm not going to talk about EIT. Well, if you see on the title, it's a bit mysterious. So I'm going to talk about reduced models. And also I'll give you a bit of an introduction first. Why would we actually be interested in using reduced models in a learning framework? And how did we actually end up there? So since it's also a bit of an overview, not used to it. Okay, now it works. Sorry. Good. So since the overview of a bunch of works we've done, there's also a lot of people involved. I wanted to credit most of them are. So we also see actually there's people from here, the University of Cambridge, of course, UCL is involved, then from KTH, the Netherlands, and even from Finland, another group that's been involved in here. So what are we actually interested in? We are interested in reconstructing images of so-called photoacoustic tomography, which is a hybrid modality. So the whole thing basically starts with an illumination. So basically you take a laser like this, but you shine the laser into the tissue in your finger, then the light distributes in the tissue, gets absorbed, and leads to here the thermalization, which leads to a local pressure increase. And that's actually where we're interested in. So for the rest of the talk, we forget about so we have an initial pressure inside the domain, and this distributes as a wave through the medium. So we have here an illustration. So here we have our initial pressure inside the medium, and then the wave distributes through the medium, and we collect the measurements on the boundary surrounding the target. And basically our measurement here, at least in a 2D setting, is a 1D plus time series. So, and from that, we would like to reconstruct then, so our measurement now given on the boundary, we would like to reconstruct our initial pressure inside. And because, well, so this is our forward problem, the forward problem from our initial pressure P0 to this time series on the boundary. I'm going to be lazy in the future. I'm not going to write this down. So we typically write it in our inverse problem setting as AX equals Y, where A is now the mapping from P0 to the measurement on the boundary. And if we actually have now a nice measurement of this surrounding the whole target, we could actually just solve the PDE backwards. And then we just basically, so we solve the PDE backwards. Do something? Yes, here, very slowly. So very carefully solve it, time step by time step. We back propagate basically the energy that we collected on the boundary back into the medium, and we get quite a nice reconstruction, a bit noise in there, but this is pretty good. Sadly, in practice, as you could imagine, we don't always have a full circle or a sphere surrounding the target. In practice, what we actually do have is the planar sensor. Well, there are actually existing other sensors, but what we have at UCL, we have a planar sensor, so we only measure from the bottom. So here we then shine the light inside the target. It gets absorbed, the pressure wave distributes back, and we collect it on our planar sensor. In fact, we still get quite nice images here. So just imagine you're looking now inside the target. So you look inside the mouse, you actually see here, this is a mouse liver. So you get quite nice images, but you see already that mostly we get nice reconstructions here on the top, but what we suffer is classic limited view artifacts, or we think about X-ray tomography as would be a limited angle setting. So we have quite a bit of information missing, so we would need to do a bit more than just solving our PDE backwards. So what we classically did were then variational methods. So, okay, So classically, we set up our penalty functional. We were trying to find a solution x by minimizing the penalty functional, given here a data fidelity term and some regularization for some prior information that we have. So what did we do? Well, very classically, we did just gradient descent. So we take a gradient step. Here is the gradient of the data fidelity term and the gradient with respect to the regularizer. And what we now do, what we want to do in the learn framework, we actually had also yesterday a nice talk by Rebecca Willett on it. We want to now do this in a learn framework. So now we take these ingredients here. We had take the gradient of the data fidelity and basically the x, because we don't want to pre-describe our prior. We take these ingredients and plug it into a network that now computes our updates. And it's basically an updating operator in an iterative scheme, using the same ingredients that we would use in a classic iterative reconstruction. And then we repeat this for a number of iterates up to n. Then we define our full reconstruction operator, which consists of our n iterates or n updating operators, and then we get our output. Yeah, we get our output after n iterates here. Good. So the main question is, how would one train this? And actually, this was nicely touched on it yesterday as well. Ideally, to get the best results, we would like to train this whole reconstruction operator together in an end-to-end manner. So all iterates together. That means we're giving data. So we have training pairs, input data, ground truth reconstructions. We could train this in a supervised manner. So we plug in the data, we have our full reconstruction operator and train this to be close enough to our ground truth. But that comes with a few limitations. And in fact, we don't only need to calculate the forward pass, but also we need to calculate, of course, the backward pass. Now, if we think about what was my problem, I'm working in 3D, and my forward model is the wave equation, which is rather expensive to actually simulate. Well, expensive in the sense of deep learning. Everything over a second is very expensive to train because you need to repeat it 10,000 times, 100,000 times, and that adds up very nicely. So end-to-end training is not really scalable to even large image domains or higher dimensions. And those are two factors. Mainly, well, we could, one limitation is just, well, we have a large volume. Memory limitations, well, we could use just larger clusters if we would have a lot of money and working for Google, or there are actually some nice approaches where we could reduce memory consumptions, either using invertible networks for iterative approaches, or just even, or here is actually an invertible unit. It was also quite nice to reduce memory consumptions. So that's one solution, but only for one of the problems. And as I mentioned, the major problem is actually that the evaluations of the forward operator become very prohibitive. And in our case, the forward simulation, actually the accurate forward simulation takes about 15 seconds. And then we need to do the backward, and then we need to also calculate the gradients. So that becomes very expensive. So what can we do? So we thought about, and our first solution that we came up with in the early beginning is, why don't we just get rid of the idea of training it end to end? We just train it in a so-called greedy manner. That means we train each of these iterates, each updating operator sequentially. That was an easy solution. And it actually worked very nicely. So that means now instead of doing this, we train now the whole reconstruction operator. We only train each updating network to be close enough, to be as close as possible to the ground truth that we have, given the output of the previous network. Of course, in terms of optimality, this is an upper bound to end-to-end training, but actually, as we saw, it worked really nicely, and it made training 3D iterative learned reconstruction possible. So what we did now, we had basically what we trained, 5 iterates, which took us still 7 days, to train. We had about a bit more than 1,000 training samples, so we need to run the forward and the join for each of these 1,000 training samples in between. But then the training of the networks itself, the updating operator, is decoupled from the evaluation of the forward operator. So that was nice. My rough calculations for end-to-end would have given me 140 days. That's not very viable. We would be still writing on this paper probably. So that was nice. And what did we get from it? So we basically got a reduction in computation times by then being able to reduce the amount of iterates that we need in comparison to classic total duration. So total duration we would, because we're not that patient, we would just run for 20 iterations. We're satisfied with that. Now we could cut it down to 5 iterates, but we're still limited by actually the time that we need to evaluate for the forward operator. So we're still at 2.5 minutes for learned reconstructions. It's better, a bit faster, but still not really viable, especially because Simon hired me to do real-time imaging. So that's definitely not real-time. So we thought, what could we actually do? Now we're coming to the actual part of this talk. Could we reduce the computation times? So obviously the bottleneck for us is the computation times of our forward model. So is there some principled way to achieve first scalability and also computational speed up using some sort of model reduction techniques? And model reduction techniques, I now understand in a very broad sense that we are just reducing the computational complexity by either using coarser discretizations or analytical approximations or more efficient solvers. Some way we need to reduce the computational cost. And just as a short side note, what we did, we actually investigated the coarser discretizations, which nicely actually captures also the memory footprint. So you can reduce the memory footprint and the evaluation time of your forward operator by doing the learned iterative reconstructions on increasing resolutions. But then you're actually still limited by the evaluation time of your final iterate. So it solved some issues, not all of them. So, but also one problem is that if we're using now these reduced models, we typically suffer a loss of accuracy. So we do end up with something that is not as optimal as I would if we would use an accurate operator and needs to be compensated for. It's maybe quite straightforward to do that in a learned framework. And also now the rest of my talk will be 2 different paradigms to do this correction, especially either we just plug it into learned framework, or could we actually now use an approximate model and correct it with a network. So, but let me just shortly talk about the approximate model so you get a bit of an idea. So now we have actually one benefit of working on the plane, and especially so if we have a planar sensor, we can use such a relation between, now here X again was our input and this is a Fourier transformed input. There's a relation, so we basically, let me put this up. So instead of using the wave equation, solving this very accurately, what we can do is actually quite nicely related to Samuel's talk before. We transform this to the spectral domain, and then we multiply. So we basically do the propagation by multiplication in Fourier space. Then we are on the spectral domain of the sensor, and we do an inverse Fourier transform on the sensor. That's nice, and especially actually is done for the inverse. But the problem is this multiplicative factor. And if we use it as a forward, we actually, this multiplicative factor has a singularity. It's integrable, so analytically not much of a problem, but in practice, if we now discretize on a grid and want to use our FFT, we actually end up with either blowups or we end up with artifacts. So what we did in practice is we thresholded those, basically the data that causes singularity, but then on the other hand, so we thresholded some data out, but then we used the FFT and we ended up with some aliasing artifacts. Still, it's an approximate model which introduces artifacts, but we're able to use it. And using now this relationship, instead of doing a full wave simulation, which we actually able to speed up more, and it's 8 times faster. So now with a reduction in iterations and a reduction in the computation times of the forward model, we end up with a speed of 32 times. We don't, so if you remember, maybe last time we had an increase of 2 to 3 decibel compared to total variation. Now we have 1 decibel still, it's quite nice. So it's a bit worse, but we're definitely much faster. Still not exactly real time, but I would just claim real time is achieved if we just reduce our image size. Then we're there. But so it's nice. So now we can use an approximate model. We just plug it in into our learning framework, we train. But what did we learn from it? Not much. We learned that we can use it. So, and that's what we call an implicit correction. We just use an incorrect model. We just need a mapping basically that goes between the data and image space and backwards. We can plug it in our learning framework. We have enough training data, we train, and it works. It's nice. But yeah, again, we're mathematicians. So we could ask our question, why does it work? Sadly, we didn't get really to the bottom of why does implicit correction work. So we thought about how could we actually approach this question in another way. So can we actually, and what we asked is, can we learn instead of just using it in a learning framework, could we actually now take our approximate model and learn a network that corrects it? Then we have a corrected model and plug it into a variational framework, use it there, and would it converge to the same point as if we would have the accurate model? So that would be the rest of my talk. Good. So now I have a bit of a glossary here, and this will blow up at the end because we're having a lot of different operators coming into this game. So what we do, as I said, we have an accurate model, we have our approximate FFT model, we have now a forward correction that operates in data space, and then we obtain a corrected model, so a corrected forward model. Ideally, of course, we would like that these are sort of, so that our corrected forward model is similar to our accurate forward model, but we cannot really expect this for all possible X. It's actually also nicely mentioned in previous talks. There is a subset, and this will basically be later our training data, with it we can expect it to work nicely on. So, and as I said, the primary question is, now given this corrected forward model, could we plug it in to our classic variational framework, use a gradient descent method, and what would we get? So let's just see what happens. So basically it means that we want that the minimizer of this will be approximately the same as the minimizer of our classic, I call it the accurate functional. And to draw connections to the learned iterative schemes, we now are concentrating actually just on gradient descent methods. So that means, so of course we need to compute the gradient of our penalty functional, and we would need that the gradients are then similar. If we just do this basic framework, we would need that the gradients ideally would coincide. So let's compute the gradient that we get with this corrected forward model. We get something like this, because while we use a neural network as a correction, so it's a nonlinear correction. So then if we apply the chain rule, so we have here now our corrected residual, we get the Fréchet derivative of the neural network evaluated at the forward projection, and then followed by the joint of the approximate model. So looks okay, but that comes actually, if we look very closely and very long at this, it comes with one major limitation. So of course we want that these are sort of equal, but the main drawback is that actually this whole, so the mapping properties of this whole thing is limited by the range of the adjoint of the approximate model. And if the range is too different of this adjoint to the accurate model, then we can't actually, we cannot achieve that these are equal for many samples. And so the problem, actually, the key difficulty is not in just correcting the forward model, but also actually achieving that we can use it in an iterative scheme, which means here the consistency of the adjoints. So then, well, we checked basically, well, you can formalize this. So in specific setting, if we now just look at the least squares problem, of course, could be solved by regularization, some of the issues, but if we just look at the least squares problem, and if the minimizer of our original problem lies outside the range, so the closure of the range of the adjoint of the approximate model, then we cannot achieve, actually, we cannot converge to the same. So that's not nice. So what do we do? So basically the problem was that, very urgent question.
No, that's a message to the group.
Okay. So we finish. So where were we? Yes, adjoint. So the problem is basically when we compute our gradient, the adjoint, we're limited by the range of the adjoint. So we thought, what do we do? Well, not the most elegant solution, but we ended up. So we don't just correct the forward, we also correct the adjoint. So that's what we ended up. So now you see it's starting to get larger here. So now we have not only a correction of the forward, so we have a corrected forward model, we also have a corrected adjoint and as a composition, and especially now the network comes after the adjoint is applied, so to correct actually for the range. And then we would need that our gradient consistency now turns into this, where we have basically this would be then our gradient, and we would need that this are sort of equal. Good. How can we use this to now plug into, actually now we have our two functionals. So we have our corrected function or our accurate functional, and we have the corrected functional using the corrected forward model. And we want to establish, can we actually know that that convergence result would be converged to something, to a minimizer or close at least to a minimizer of our original functional. So for that, we're actually looking now not just that the gradient always coincides. We rather actually look at an alignment condition. So that basically we want that now our corrected gradient points in a similar direction as the original gradient, at wherever point it is evaluated. So that's what we look at here. So of course, if these are equal, then this would be 1. So they're showing in the same direction. Then we would definitely converge to the same point. So as I wrote, a bit of abuse of notation now, we consider the gradient of the, how did I call it? The corrected functional as this composition where we have the corrected adjoint and the corrected forward one. So with that, actually, it's quite straightforward to just to establish that we can converge to the same neighborhood. So X is now the minimizer of our accurate functional using the accurate model. If this, if the gradient points in a good enough direction that is greater than some positive constant, we will eventually converge to some neighborhood of our minimizer of our accurate function. So that's quite nice, but it's not very useful if we want to compute anything, this quantity. So we did a bit of, and that actually Sebastian did, Sebastian Lunz, who was a PhD student here at Cambridge. They did a bit of analysis and we reformed this into something that we actually can use for the training. And we ended up with this. We can now bound the angle between the gradients by something that has the approximation error in there. And this is the approximation error of the forward model, and this is the approximation error depending on the forward model, but this is the approximation error of the adjoint. So now we can actually, if we train now just straightforward supervised, we would have a bound on these and we get up with an alignment condition on our convergence. And then just combining, if we combine the previous two, we then get to our theorem that we would, so of course we need a bit more, so we need some constants that are bounded. We have the condition on our forward approximation, and we have the condition on the approximation of the adjoint. And then we would eventually converge to a neighborhood, minimizing the corrected functional. We would then converge to a neighborhood of the minimizer of the accurate functional. That's quite nice. So now we wanted to test this as well. Good. How do we train this? Yes, training is another question. So, so reminder, we have these compositions. So we would train then in a supervised manner. Basically, we only need the samples and we need knowledge of the accurate forward model. Then we can simulate our training pairs. So the problem is, of course, already as you see in practice, to train this whole thing, you would need to actually evaluate your forward model in the training procedure. So it's not yet really practical. And so it's important, so we can train the forward model, but also it's for the adjoint fit, it's important that we actually train on directions that are relevant to our minimization scheme. So we kind of need to know what we are going to minimize to actually train this thing. So it's not exactly practical, but that's not only why we did it. So these are actually very important, that we train this on directions which are relevant to the minimization procedure. And in fact, we actually trained it later even on a recursive scheme, so that we trained it along the trajectory of the minimization. So we need to evaluate actually iterates of our original minimization algorithm and use these for the training procedure. So it's not exactly practical, but at least it worked. So that's what we also did only in 2D. So we trained it in 2D on a limited view scenario again. So we have here our now linear sensor, not planar anymore, just a line sensor. We use our FFT model as the approximate model. And we trained it then on 2 simulated data sets, so very simplified, just circles with different brightness, and then on more realistic vessel phantoms. And we used just a total variation as regularization classic. Good. So here we have a comparison of the results for this very simple case. Here we have the approximation error method, which is a linear correction. So it's basically linear statistical correction, which does a reasonably good job. With the uncorrected operator, as expected, we would get a lot of artifacts and a lot of blurring on the sides. Then if we only train the forward, we get these and some artifacts on the bottom, where the algorithm didn't really know where to put them. But the forward adjoint, we get a bit better, at least in terms of artifacts in the background. But then, as I said, it's important to train on relevant directions of your minimization. So if we do that, we actually get for the forward correction alone and the forward quite a good result as well. Then for the forward adjoint, we get here quite nice results. We can also formalize this on this quite overloaded graph. Important ones are here on the bottom. So this would be using the accurate model. And we see with the forward correction, we actually then nicely converge to something that is close. And this is actually the data error. And here's the reconstruction error. So the data error is actually quite good. So if you see that you only correct your forward model, you still get quite a good data error. But in terms of reconstruction error, you do decline a bit. And here's something interesting happening. So here we see that first, if we only train without these important directions for the training, it first declines, but yes, and then actually it starts to diverge a bit. And if we check now the alignment condition, it was very interesting. I forgot to put it in here. It was very interesting to see that if we follow now this curve and the alignment of the gradients, we see that here at this point, it changed to negative alignments. So actually, we also saw that the trend changed to negative alignments and then it started to diverge. Okay. So let's have a look also on the measurements. So here is that would be true, the accurate measurements. Here we have the approximate, so now we actually see nicely our analyzing artifacts and the corrected ones, even actually here threshold some of these reflection artifacts out. And we also see actually the gradients are nicely fit. So that's here you have a lot of these streaking artifacts, so the analyzing artifacts, which are removed in the corrected gradient. So for the vessels, things get more difficult. Also 2D is a very difficult problem for photoacoustics, the limited view problem. So here the problematic areas are down here. So these are very hard to reconstruct, just in the bottom where it's almost nothing detected. Over the accurate model, we get a reasonable reconstruction, but you actually see that even here we can't really reconstruct the bottom. Of the uncorrected, there's a lot of information missing here. Approximation error method does a good job, and generally, actually, all of these corrections are doing reasonably well. There's a bit of some artifacts actually still sadly remaining here, but the bottom parts are getting a bit better. It's very subtle, very subtle. Okay. But one nice thing actually is, now that we are back in a variational framework, what happens if our noise actually changes from the case that we trained on? Now here we have also, again, this is a very difficult problem, just in the bottom. So we measure here on the top. So just imagine you really don't have much what you see here. If we use the uncorrected, so just the approximate model, it's pretty bad. If we do our full framework of the forward joint of the parameter that we trained on, it gets a bit better, but it's pretty messed up here. And if we adjust the regularization parameter, actually we increase the regularization parameter that we get a larger regularization here, we actually get a very reasonable reconstruction for this rather difficult case. So at least we retained some of these properties that we know from regularization theory, that we can adjust the parameter, even if the network, the forward model, or the whole forward and joint correction was trained on a different setting. So to wrap up, some final thoughts. Well, approximate models, at least if we think about three-dimensional or very high computationally expensive problems, if we want to use, at least if we want to do learned image reconstruction in a model-based setting where we use the model in the reconstructions, it is necessary for speed up to consider some computational improvements to your model. Implicit corrections, if you're just interested in getting good reconstructions and just getting it to work, you have training data. Implicit corrections work well, but are still difficult to analyze. Maybe we're getting there someday, but not so soon at least. Explicit corrections, we could. So we have investigated that we can train an explicit correction, we can plug it back into a variational framework, and we still get convergence results, or a result on that we actually converge to the minimizer that we would expect under normal conditions. Primary limitation, it's not really practical because the training procedure is very expensive. We need to know the accurate forward operator, and we need to train it on directions that are relevant for the minimization process. But our theoretical analysis, one takeaway that we, at least for us, take away, using approximate models, it's not only important to correct the forward, but it's actually important to correct in the directions that you're going, which might, or the forward adjoint did here the job, which might to some extent explain also why primal dual methods or the learned primal dual methods are doing so great in the learning framework, and might be actually a solution to use in the future. Again, we only end up with the end-to-end problem. We can't really train these end-to-end for a large amount of iterates. With that, I thank you for your attention, and
thanks a lot, Andreas. Good.
Thank you for the interesting talk, Andreas. I think I have a question about the need to have a good correction along the path of your gradient descent. So I understand this is because all your approximations are local, so you only know the forward operator on the manifold or around the manifold of the training samples, and also they are joined. You only know on the manifold of the training samples where they are joined. Why don't you adjust the gradient descent so that you only move along these manifolds? So you sort of you project your gradients onto the tangent plane or do something else, but you enforce by design that you move only along the manifold given by the training samples. And then perhaps you will not need this condition.
Well, that's a very good suggestion. I guess we didn't do that because, well, we didn't think about it. The biggest problem, so just to shed some light on it, what we saw is that, so in the later iterations, the images that the network sees do change very drastically. So if you think about your minimization in the beginning of your total variation, you would first have maybe a sharpening or mostly noise removal, and at the end, actually mostly the noise removal in the beginning, which corrects also the contrast, and at the end you have very subtle changes in the side lobes. So it was important that we actually have the whole manifold that is relevant for the minimization, that we show it to the actual networks. If we could have done it a better way, most likely, but at that point we didn't think about it.
Thank you.
Thank you very much for the talk. I have a question regarding this corrected adjoint. Will it in the end have something to do with the actual adjoint of the perturbed operator or not? Because I mean, if it's not a real adjoint, then I was asking myself how to interpret this gradient descent-like method. Because if yes. I mean, you take the yes. gradient and then like your adjoint is not a real adjoint, so how to interpret the things then?
Yes, I think the only thing that we can say there, it's definitely not the adjoint anymore, because also we do have the corrected forward model, which has the nonlinear correction in there. So, and then what the corrected adjoint is really just a nonlinear operator that is trained to fit that basically the gradients align. We can't think about it as an adjoint anymore. Yes. But the only thing that we can think about it in the sense of gradient descent is that we need to have this alignment condition that it points into similar directions.
Maybe you can interpret it as some kind of preconditioning then, or something like second order things where you change the direction of the gradient or something. I was just wondering because, like,
I mean, it's non-linear, so it's difficult, it's difficult to put any of that.
Getting everything gets very confusing.
Okay, thank you.
Yeah, thank you for the comment.
So thanks for the presentation. I wanted to ask just a couple of clarifying maybe questions. When you show this first phantom with a bulb, and then you say that, okay, here's my data and here's the approximate data. When you do the reconstruction, do you then use the approximate data or the accurate data to perform the reconstruction?
How you mean for the measurement? Okay, the measurement that we have, we start with, okay, yes. So we assume that this would be, what we get from the measurement device. So yes, this would be, we assume that we have, or with noise, of course, we assume that we have this. Yeah. Okay. And we're working with an operator which would give us this if we don't correct it.
Yeah, and you were correcting it by just comparing it to the accurate.
Yes.
Yeah.
Yes.
And then a small question, just where is the sensor at the top? So
yes.
So the further the object is from the sensor, the more difficult it is.
Yeah. So basically, so as I sort of kind of hinted, the difficult areas are everything in the bottom and especially here in the corners. The data distributes as a circle. And if you think the point source that is down here is basically just detected as almost as a straight line at the sensor. So you don't really know where from down here it comes from.
Yeah.
That's why it very much blurs out. You can see this in one of the, I think, look at it. That's why we kind of have these side lobes here. That's quite typical. These are the sort of the limited view artifacts in photoacoustics.
Any more questions?
I think there's some. In
The question was about references.
Oh,
I put the one.
yes.
You want to put some more in?
I would have a question.
Sure.
Please.
So you learned an approximation to the forward operator and you learned an approximation to the gradient of the fidelity term, right?
So we did learn a correction of the forward and we learned a correction of, well, basically, yes, we learned a correction of the gradient given the correction of the forward. So
yeah,
the sort of composition, yes.
Would it be possible to learn this corrected gradient not as a separate network, but use the loss function for the gradient field given by the corrected forward operator? Does that make sense?
Oh, would this be? I'm not sure if I fully understand that.
So you learn a correction for the gradient, and you learn an approximate gradient. You learn an approximate forward operator, right?
Okay, let me try. We learned, so yes, so we learned here at least the correction of the forward, and yes, we sort of learn a final network at the end that corrects this whole term.
Right. Yeah.
Yes.
Could one get rid of the G network by and just basically put all the load on the F?
But that's sort of what we did in the beginning, and then so if you just take a gradient approach, so there might be better ways to do this, of course. So if you just do that, if we only have everything on F, we end up, that was the problem, that we end up in the final, where if we compute out the gradient, we end up with the adjoint at the end. So basically, the whole mapping of this is limited by the range of our adjoint. So that was the problem what we ended up with. Maybe I'm misunderstanding the question.
Yes, you'd have to use a zeroth order method, then you wouldn't need the
Well,
gradient.
that would be an option, yes, if you don't compute.
But you could also compute the gradient of the approximated forward operator, right? And that would be basically you don't really need the adjoint. You only need the ability to create a scalar a matrix vector product between the adjoint and some vector, right? And that could be, you could compute that by taking the derivative of basically the approximated forward operator. Maybe I'm misunderstanding something.
I think it would be good if we could write this somewhere down together.
Yeah.
Yeah.
Well, we're going to have a discussion session tomorrow where we will be
yes, I'm happy
using.
to talk about this
writing.
more later, or personally.
Yeah, cool.
Maybe
Thanks.
clarify this more. Thank you.
Sure.
Okay, are there any more questions? I think we're just a little bit over time, or I mean, right on time and a little bit more. Let's put it like that. So let's thank Andreas again. Great. See you back in 15:30. from London, then I go from